Okay, students, welcome to video class 31. And in this video also we are continuing our study on Bode plot, and that's part 4. And we'll do one more, another question. The open loop transfer function is given by the expression g of s h of s equal to 30 by s into 1 plus zero point 0.5 s into 1 plus 0.08 s. Draw the Bode plot, or the first one question is obtain the Bode plot of the above transfer function and comment on its stability. Okay. Now the second point is find out gain margin and phase margin. Okay, and phase margin, right? So let's start with this. So step 1 is to obtain what? Obtain the sinusoidal transfer function. Obtain the sinusoidal transfer function. And when you look at this open loop transfer function in the S domain, you can see that this is a Bode form. Bode form means these factors, that is the first order factors, has to be of the form 1 plus something into S. So this is of that form, therefore this is in Bode form. Now what you need to get is you need to obtain the sinusoidal transfer function. Now this is obtained by putting S is equal to j omega to this g of s h of s, so that this becomes g of j omega into h of j omega is equal to 30 divided by j omega into 1 plus 0.5 j omega into 1 plus 0.08 j omega. Okay. Now we can identify. So this is so we can identify 4 different terms. That is a constant term. Then you have a 1 by j omega term. Then you have 1 by 1 plus 2 first order terms, that is 1 by 1 plus 0.5 j omega, and another one is 1 by 1 plus 0.08 j omega. So what must be your step 2? Now step 2 is you need to find out the initial slope of the Bode plot. The initial slope of Bode plot, right? Now that is given by, that will, so such an information you will be getting by k by j omega. Generally we say it is determined by k by j omega raised to n. Now in this problem this will be determined by 30 divided by j omega raised to 1, meaning first of all what you should understand is it is a type 1 system. Now why do you need to understand this type 1 system? We have already studied, so I'll be showing that previous slide. Look at this. So for a type 1 system, the k is found out to be equal to omega, or the frequency at which this magnitude plot touches the 0 dB line at omega is equal to k, right? That's for the type 1 system. Now for a type 2 system, the omega becomes root k. For a type 3 system, it is the cube root of k, and it goes on like that. And for an n type system, omega is equal to k raised to 1 by n. Okay. So that means in this case we can say that the omega, or the frequency at which the gain plot, at which the k by j omega of this problem meets at 0 dB will be equal to the value of k, because it is a type 1 system and you know how to derive that. So for a type 1 system, it is equal to k. That means the omega of this k by j omega is equal to 30 radians per second, right? So this is omega is equal to k, that means it is equal to 30 radians per second. Now, if you know the point at which this k by j omega passes through the 0 dB, and from that you can find out the initial slope of that Bode plot. Okay, right, and we'll do that in a moment. Okay, now after finding out, so this is all about the initial slope of Bode plot. Now, initial slope means it is at the rate at which it moves. Now, how to find out this omega? So, initial slope will be, what will be the slope? And the initial slope will be, because this is k by j omega, or the initial slope of 30 by j omega will be equal to 20 decibel, yeah, minus 20 decibel per decade, right? Because it is of the form k by j omega, and we have already seen that it offers a, yeah, it uh, offers a fall of 20 dB per decade, because it is a type 1 system, and this 20 dB per decade line meets at the 0 dB at a frequency equal to 30 radians per second. So these are the two informations that you need to get of the initial slope. One is, it is the initial slope, the frequency at which the initial slope touches the 0 dB. The another one is the slope, and the slope is minus 20 dB per decade, because this is a type 1 system. Now, had it been a type 2 system, this would have been minus 40 dB, while omega will be root of 30. Okay, right? Okay, that's it. Now, next, coming to the next step, the step 3 is to find out what? Is to find out the corner frequencies of the first order terms, okay, right? Now, how many first order terms you have? One is 1 by 1 plus 0.5 j omega, right? That is the first order term. Another term is 1 by 1 plus 0.08 j omega. Look at this. So you have 1 by 1 plus 0.5 j omega and 1 by 1 plus 0.08 j omega. Now, what will be its corner frequency? Now, how to find out the corner frequency? The corner frequency is actually the reciprocal of the coefficient that comes along with j omega. Okay, so in this term, the coefficient of the j omega of this part is 0.5. So your omega corner 1, let us call this as corner 1 frequency, which is equal to 1 by 0.5, or this is equal to 2 radians per second. Am I right? Okay. Then next is omega corner 2, and that will be 1 by 0.08, right? This is equal to 12.5 radians per second. So it is exactly what we have got in the previous problem, right? Right, exactly what we got it in, that is 2 radians per second and 12.5 seconds. But what is actually the difference between the first and the second problem is, you are having exactly the same problem, 4 divided by s into 1 plus 0.5 into 1 plus 0.08 is, but in the second question we have changed the constant, or the forward gain, or the gain factor, from 4 to 30. So we are going to study the effect of increasing the, so you are having exactly the same problem. Both are type 1 system, both are having the first order term same, but they only differ in their constants. Now let us see what's going to be its impact. So as we have done in the first question, we got the corner frequencies to be 2 radians per second and 12.5 radians per second. Okay, so that's it. Now, next step 4 is to obtain the magnitude plot by using the following things which we have already found out. That is, the initial slope of minus 20. The initial slope will be minus 20 dB per decade, which meets the 0 dB at 30 radians per second. So you know how to find out that. Now that means the Bode plot is before meeting these two terms itself. The Bode plot is having an initial slope of minus 20 dB per decade. Now at 2 radians per second, what happens? This term will come into play. So this Bode plot is already having a minus 20 dB per decade due to 30 by j omega term. So what will be the cumulative slope? Cumulative means after 2 radians per second, what happens is the Bode plot now moves at a rate of minus 40 dB per decade. Why minus 40 dB? This 1 by 1 plus 0.5 j omega offers an extra minus 20 dB per decade to an already fallen minus 20 dB per decade. So altogether you have minus 40 dB per decade after 2 radians per second. Now after and it will go till 12.5 radians per second, and after this 12.5 radians per second, this term comes into play, which again offers another minus 20 dB per decade. So in turn it gives you minus 60 dB per decade. Now using this, let us try to draw the magnitude plot. Okay, now how to prepare the semi-log graph paper for this Bode plot. So as I have explained, so you have one axis to be in the logarithmic scale, and in the vertical axis, when you go through this vertical axis, you can see that this is a normal graph. Okay, equal divisions, while when you move in a horizontal direction, you can see that each divisions are not uniform. So the divisions are not uniform. That means these divisions are logarithmically scaled. Now this is how. So first of all, let us see the magnitude. So on the left side, this axis is being assigned for this magnitude, decibel, and this is axis are common to both the magnitude as well as the phase. We'll come to that later anyway. So this is of the anyway, it's a logarithmic scale. So that all you know. Now the next thing is this point. I mean, you can have a different, I mean, you can start with, as I told you can start with 0.1. If you start with 0.1, then this will be the next decade. That is 0.1 into 10, that will be 1. Then this will be 10, this will be 100, and so on. Now you can start with 1, then it will be 10, it will be 100, 1000. Or you can start with 10, then it will be 100, 1000, and so on. Now this is determined from where will you start this frequency axis. That will be determined by the already found out corner frequencies and the meeting point of the initial slope at the 0 dB. Now we know that 30 radians per second, which is well above this corner frequency. So the minimum frequency is the first corner frequency, or the corner frequency corresponding to 1 by 1 plus 0.5 j omega. So we need to have a graph which includes this 2 radians per second. That means if you need to include this 2 radians per second, this has to be 1. Okay, this has to be 1. The next decade is 10, next is 100, and it goes on like that. Now we know that which meets at the initial slope of minus 20 dB per decade meets at 30 radians per second. We know that this decade consists of frequencies 1 radians per second. This starts with 1. This is 2, 3, 4, 5, 6, 7, 8, 9. Now once it reaches over here, this becomes 10, right? Now the next decade is 100. That means each point is going to be into 10, right? 1 into 10. So this will be 1, this will be 10, this will be 20, this will be 30. So this is actually the point of concern now. This 30 or this represents the 30 radians per second point. So you can make use of that scale, right? So this is 30 radians per second. Okay. Okay. So I'm just marking over here. Okay, you may try to draw it accurately, otherwise the results can be wavered result. Okay, as far as possible, draw it very accurately by using a scale and so on. Okay, so mark this point. So this is your 30 radians per second. Now we have an initial slope of minus 20 dB per decade which passes through this point. So you can actually plot what? Plot a minus 20 dB per line which passes through this 30 radians per second, right? Say if a line is passed which is having a slope, means that slope will be always the same as it moves through this line, so that you can have a how to find out the line which line of minus 20 dB per decade which passes through this line. So of course we can find out from this point the next decade is going to be this one, right? So this is 30 radians per second. This has to be 300 radians per second. So what's the correlation of these two frequencies? These are a decade. That is 30 into 10 will be, you will be getting 300 radians per second. So this is a point. So this one, when you look at this, okay, when you look at this point, this actually corresponds to what? This corresponds to 300 radians per second, right? So this is 300 radians per second. That means as one moves from 3 to 30, he will be arriving at this point, and this point is called as a decade. Okay, now as the say a line is passed through this point, so as this line moves from this point to this, it will be reaching at a point again at minus 20 dB per decade. So how will you draw this? Now from this point, how will you plot this minus 20 dB per decade? This is minus 20, right? So you can have this. This is minus 20, and the corresponding point you can mark over here, right? Okay, so that's it. Okay, so look at this. So a line is so this line, okay, this is what we are talking about. Look at this. So this is a line which passes through this point. That means it is having a minus 20 dB per decade. How will you understand that? See, this line is passing through this point, and it is moving in such a way that it comes to meet at this point. Now what is the speciality of these 2 points? This is 1 decade, right? This is 30 radians per second. This is 300 radians per second. So once it reaches this, its slope will be again minus 20 dB. So that means this is going to have a line which passes through this. This is always having a what? Having a slope of minus 20 dB per decade. Okay, but you should not draw like this. You should draw by dotted lines. Okay, so I'm just showing it anyway. Don't make it so bold. Okay, so draw it very lightly. Okay, so this is actually the line which passes through. So this is having a minus 20 dB per decade, right? This is having a minus 20 dB per decade. So this is actually the initial slope. Now, so it is found out to start from 1 radians per second. We are not worried about this point anyway. We just want to know how it starts. So it starts like this. Now from the corner frequency, it is found out that this will be having an initial slope up to 2 radians per second. So what is the 2 radians per second? This is actually your 2 radians per second. Now using that scale, okay, using that scale, Okay, this is it. Okay, look at this. So till this point, this will be having what? This will be having a 20 radians per second. So I'm going to make it bold. Okay, you need not to want to use pen. You can use only pencil, and these lines you can represent this as by dotted lines. That is more advisable. Since I'm using a pen only, I'm using this as pencil, so I'll be able to ball this. You can use your pencil only. So use this initial slope by using dotted lines. Okay. Now, anyway, the thing is that these lines should not be bold. Only the required plot has to be made bold. Okay, so that is left to you. You can do as you like. Okay, now this is it. So this will be this particular. Now this particular this thing, right? So this is it. So this is a point till the initial slope. This is, so you must write this initial slope to be 20 dB per decade. On this line you should write like this, and this is having a 20 dB per decade up to 2 radians per second. After that it is having a minus 40 dB. Now how will you do that? So from this, now this is your 2 radians per second. Now what is the next decade? Next decade, this is 20 dB per decade. Now you can have the corresponding point. So mark like this. You can have the corresponding point, say somewhere over here, right? So this is actually one decade, right? This is 1 decade, the corresponding decade. Now you must find out the corresponding. Now from this onwards, from this point onwards, it will be moving at a rate of minus 40 dB per decade. Now how will you do? How will you find out? Now you can take the corresponding point under this section, so that will be offering a minus 20 dB. And on the next section, if you can find out this corresponding point over here, then that point will be giving you minus 40 dB. So as it moves from this frequency to this frequency, this will be reaching somewhere over here. So find out that point. Now for that, it will be nice to start from here. So you have a 3 division. Okay, when you count those 3 divisions over here, that becomes a 20 dB. Similarly, when you count those 3 divisions over here, you will be getting a minus 40 dB. So that can be drawn as follows. Okay, now we have already found out that. So look at this. So this is actually your decade. Now as this Bode plot from this point onwards, because of the effect of 1 by 0.5 j omega, this will be offering another minus 20 dB per decade. So this is minus 20 dB per decade. So altogether you will be having a 40 dB. So as this Bode plot moves from this frequency to this frequency, this point will be reaching, okay, somewhere over here, right? So this is actually the minus 40 dB per point. So as it moves over here, this is 20 and another 40. Okay, so now let us see. Anyway, we can see that from this figure itself, you can see the slope, right? So this is it, right? Okay. Okay, so now this will be moving up to 12.5. Now we know that this is 10, so this must be 20. So this will be moving up to, this is having 10 divisions, so this is 10. If this is 10, this must be 11, 12, 12.5. Okay, so till this point, this particular wave will be having what, this particular border plot, this, so that means this is 11, 12, 12.5. So okay, so I will be marking that point on this border plot. So this border plot will be traveling till, okay, I'll be showing this. Okay, so that means this is the point. Okay, now till this point, this particular wave will be, this particular border plot will be having a minus 40 dB. So I can make it bold till this point, right? So that means this is your minus 40 dB per decade, minus 40 dB per decade. Okay, so this is minus 40 dB per decade, and this travels in this way up to 12.5 radians per second. Okay, now similarly you can draw minus 60 dB per decade, and that will be drawn as, okay, so you can draw this minus 60 dB from this point. I have selected that one decade. Now the corresponding, find out this corresponding point between this. So that is found out to be somewhere over here. So that means that is offering a minus 20, and this point will be offering another minus 20, so minus 40. So this is the point corresponding to minus 60 dB. I have plotted over this decade, and keeping a scale, I have drawn this two, connected these 2 points. So till this point 1 by, we know that 1 by 1 plus 0.5 j omega comes into play, and it will be operating till this 12.5 radians per second. After 12.5 radians per second, then this term will also come into play along with this initial slope, as well as 1 by 1 plus 0.5 j omega, which offers a minus 60 dB per decade. So hope you understood how to draw this slope. Okay, now the next point what we need to find out is this from this border plot. So this is how you are to plot the border plot. Find out the border plot or the frequency at which it touches the 0 dB, and that is what is called as GCF. That means you need to find out this particular point, right? And this is your GCF, or gain crossover frequency. Now let us see what is this gain crossover frequency from the border plot. So you'll be getting a GCF of 7.3 radians per second. So you need to be very careful in selecting, in finding out this decibel, this slope. Okay, it has to be so accurate. If there is any change, that will be having some variations. You won't be getting exactly the 7.3. Okay, so as far as possible, use very sharp pencils and a big scale, so that this should not have any changes. Now another point, say suppose how to draw, in other words, I'm going to, I mean, sometimes this particular point may be having, I mean, this method of finding out the slope, you may be finding out it as inaccurate, it's not accurate enough. But I will show you one method by which you can plot this. Say for example, if you want to plot this 20 dB per decade from this point, or let us see, from this point I want to plot 40 dB per decade. Okay, now to draw it accurately, there is a method. Say no, okay, coming to this area, so you can make use of this area. You know this is a decade, right? Now if I go into, so I'm using a pencil right now. Now this is the, okay, so this is the point, this one is another point. So what is the specialty of these 2 points? This is a decade, right? So this is a decade, and this is a 0 dB line. So that means this will be your 20 dB, and this will be your 40 dB. Now how to draw this minus 40 dB per decade? Now if it is so this is actually the corresponding to minus 40 dB. So if if you draw a line, this will be what? This will be always having a minus 40 dB per decade, because you're drawing in a decreasing manner. Now if you draw like this, this is an increasing graph. That means this will be plus 40 dB per decade. Now if you draw like this, what is this? If you draw like this will be minus 20 dB per decade. Okay, so now keeping this, okay, so now keep a scale like this, okay, and you set square exactly parallel to this line. Now if you move, so keeping this scale intact, what is this line? This line will also be, it is a parallel line, right? So this line will also be having a minus 40 dB per decade, and you are moving, and make sure that the scale won't change. Okay, this has to be, so if you connect this point, right, this will be minus 40 dB per decade. Okay, this will be minus 40 dB per decade, right, because this is parallel. Okay, so the parallel lines will be having the same slope. That's the concept. So you can make use of a set square and scale to draw the accurate result. So as you can see over here, even my drawing itself is not accurate. See, when you look at this, you can see that there is a slight change. Okay, you can notice a slight change. Look at this, right? This has to come over here. So that's why I told you this method, right? So that means that will be meeting somewhere over here. So if you find out, this will be 7.3 exactly. So I think I suggest always try to draw the parallel lines like this. So it's nothing but draw similar. I mean, this is very easy to find out the minus 40 or plus, because well-defined points are there. Now you have this slope, and using the set square and scale, you can draw that parallel lines to this slope, so that will be pakka. So that will be more accurate than this, than finding out the different decades and so on. Okay, so if you can practice in that way, you will be getting a perfect answer, or so you will be getting, so 0.3 radians per second. Now as I have drawn, I have found out actually it's not 7.3, I think. Okay, so it comes around 7.5 or 7.6, so there will be variation in that. So as far as possible, so my suggestion is always try to draw parallel lines by using set square and scale, and that will only give you a accurate result. Okay, so your GCF is 7.3 radians per second. Now the next step is to obtain the phase plot. Okay, now obtaining the phase plot is, first of all, you should find out angle of G of j omega, H of j omega. Okay, anyway, you are going to get the same phase as that of this. Why? Because it is immaterial whether the gain is 30 or 20 or 4, whatever may be that the gain, the phase of always the phase of this term is going to be 0. All other terms are exactly the same terms that we have done in the first question. So your phase has to be minus 90 minus tan inverse omega minus tan inverse 0.08 omega. So this will be minus 90 minus tan inverse, okay, 0.5 omega, right, and minus tan inverse 0.08 omega. So you know how to find out this. If you have any doubts, you may just refer those previous videos. So that phasor plot can be drawn as, okay, so you're going to get the you can have the tabular construction by using the various frequencies. Now I have I mean, we have, since we have done this, you can make use of the first problem, the data from the first problem itself. It's exactly the same. Now how to draw this? It is exactly as we have seen. So this has to be this. So this is the axis where you need to plot your face. Okay, where you need to plot your face, and this I am treating as, this axis is treating as minus 180 degree. Okay, this will be minus 180 degree. Okay, so this is minus 180, this one will be minus 150, and this one will be minus minus 120. Okay, 120 degree, minus 150 degree, minus 180 degree. This one is minus 210 degree, and this will be minus 240 degree, right? Minus, this will be minus 240 degree, and so on. Okay, you can make use of this, and from this you may find out, you can convert this or transform this table into this graph using this as the phase axis, starting from this radian, I mean omega. Omega is 1, 2, 8, 10 and 20. So you can plot. If you have any doubts, you may just refer those previous video. Okay, so this can be plotted as, okay, so you will be getting a graph like this, exactly as we have found out previously in the previous. So you can just go through that, and you can see that as we have got in the case of previously, this PCF will also be 5 radians per second. So hope you understood why there is no difference in PCF, because the only change in this question is the constant, and constant is not, or the gain, that gain is not going to affect the phase. The only parameter that it affects is the magnitude. So that's why we got a different magnitude, and your PCF is 5 radians per second. Now from this you can find out that your PCF or GCF is greater than PCF, and which we have already said that this is the condition for the system to be unstable, right? So this is unstable. So as you can see in this figure, so look at this. This is PCF. PCF is anyway less than this GCF, so this made the system to be unstable. Now what we have seen, so I'm going to conclude this. Now in the first question, as I have mentioned earlier, that there is only one change. That is, in the first question the gain was 4. So as long, I mean, it was 4, and you have found out that GCF is well less than this PCF, right? It was 2.7, and this one is 5 radians per second. But as you change that 4 to 30, what happens is this magnitude plot, when you check the magnitude plot, what happens is, so when you compare these two figures, the previous figure and this one, you have a magnitude plot below this phase plot. Now because of the impact of that gain, because the gain, so this is actually corresponding to gain of 4, right? This is the gain of 4, right? While this magnitude plot is a gain equal to 30, right? Now what happened is, as you increase the gain, the phase plot remains as such, but the magnitude plot just began to rise. Okay, or this gets shifted. That's the right word. So this plot in the previous question, this is the plot in the previous question. This, what happened to this is, this one gets shifted, and it gets shifted beyond this phase plot, so thereby making your GCF greater than PCF. Okay, so that's it. So that is your GCF is greater than PCF, and that means that is an unstable system. Okay, now let's find out what is this gain margin. Gain margin is nothing but it is the negative of gain at PCF. Now what is your PCF from this figure? From this figure, your PCF is 5 radians per second. So you may just mark here to find out what is the gain, and you should take the negative of that. Okay, so while finding, okay, now look at this. At PCF, what is its gain? So this gain is one division will be the all over the division is 20 dB. So one division will be 10 divisions. So each division denotes 2 dB each. 2 dB, 4 dB, 6 dB, 8 dB, and it comes in between this. So this must be plus 9 dB, right? So this is plus 9 dB. Now what is GM? Gain margin is the negative of gain at PCF. So this is equal to negative of 9 dB, right? So the answer is minus 9 dB. So what it denotes is the gain has increased by 9 dB. So that made actually an increase of minus 9 dB made this system unstable. Now what does this suggest? This also suggests to the designer that if you can decrease the gain corresponding to minus 9 dB, this system can be brought to or this system can be made to a to a stable system, or you can make that instability condition to a stable condition by ensuring that the design is well below 9 dB from the present scenario of how much it was 30, and if you can reduce that gain corresponding to a 9 dB, then that system can be made a stable system. Okay, now what's the next thing? Now the phase margin, that's your second question. Phase margin is actually equal to 180 plus, right? Phase margin is actually equal to 180 plus the angle of G of j omega, H of j omega at GCF. So that also you will be able to get from this graph. Okay, so I have drawn the corrected this thing. So this will be at GCF becomes at 7. So this is it. Look at this. So this will be 7.3, and the phase plot comes over here. So this is your phase plot. Okay, now the phase is calculated as, okay, now if you have plotted this gain plot very accurately, you will be getting an answer 180 plus minus 207 degree. Okay, 180 plus minus 207 degree, which is actually equal to minus 27 degree. Okay, so your phase margin is negative, gain margin is also negative. This also proves that the system is an unstable system. For a stable system, we have already studied in our live class that gain margin and phase margin are to be positive. So hope you understood the impact of gain. As the gain increases, there is no problem in gain increasing, but only make sure that your GCF is always less than PCF. But in this problem, we have seen a different scenario where GCF becomes greater than PCF, and that made the system unstable. And not only that, one more point is from the gain margin, especially if the designer is so careful I mean, if you can reduce this gain to 9 dB, then you can make this system a stable system. Okay. Okay, now based on this problem, we are going to classify these transfer functions, or it can be classified as classified into 3 varieties of transfer functions. So number 1 is minimum phase transfer function. Now what does this minimum transfer function? Minimum phase transfer function is actually a transfer function with no poles, poles and no zeros. It's very important. No poles and no zeros at the right half plane. Okay, so that means if you look at these two examples, right, you can't find any, right? If you equate this, s is equal to 1 by 2, s is equal to 1 by 0.08, right, minus. So all these, if you try to plot the poles and zeros here is no zeros, only poles. The poles will be like this. It will be, say, some at 2, minus 2, and at minus 12.5. So all these poles, and same is the case in the first question also. So these type of transfer functions with all the poles and zeros on the left half. That is, there is not even a single pole or a zero at the right half plane. That is, if you have a plot, say something like this, if you have no poles and zeros in the like this, if you have a configuration like this, then such type of transfer function is called as a minimum phase transfer function. Now the okay, so that will be, say, something like minus 1 by t1 or minus 1 by t2. Okay, so this is it. So that means this particular transfer function is called as a minimum phase transfer function. And the next one is what we call as the non-minimum phase transfer function. Non-minimum phase transfer function. Now, how will you define that? A non-minimum transfer function is there must be at least will be having at least one pole or zero in the RHS side of the S plane, RHS of S plane. That is called as a transfer function with at least one pole or zero on the RHS of the S plane is what is called as a non-minimum transfer function. And this will be of the form, say, 1 plus st1 divided by 1 minus s. Okay, or say, look at this, 1 by or this will be, say, 1 minus st1 by 1 plus st2. So in this case, when you find out this the poles and zeros, when you get the numerator to 0, you will be getting this as 1 minus plus 1 by t1. Okay, so call this as z. And when you find out the pole, your pole will be minus 1 by t2. So you can represent this scenario like this, right? So the zeros will be in the positive direction, so that will be, say, plus 1 by t1, while this will be minus 1 by t2. It may be somewhere, it need not be equidistant even. So this is it. So this is a condition where one of the zeros, at least one pole or zero in the right half. So this transfer function of this form will be called as a non-minimum phase transfer function, while another this minimum phase transfer function will be of the form, say, 1 by 1 plus st1 divided by 1 plus st2. So when you take the zeros, what will be that? This will be minus 1 by t1. Okay, now when you take the poles, you will get this as minus 1 by t2. Okay, so this is it. So these are the two different transfer function. One is minimum phase transfer function, other one is a non-minimum transfer function. Now if you try to plot the Bode plots of minimum phase, okay, for a minimum phase Bode plots, generally this is just a generalization. So you will be getting this as in this example, okay. So if this is if the transfer function of this form, then the poles and zeros are on the right half. Now if this is the case, then when you try to start the plot the magnitude plot, this will be starting from 0 dB, and it increases at a rate of minus 20 dB per decade at the frequency 1 by t1, and at the frequency 1 by t2, okay, at the frequency 1 by t2, this remains a constant. Why? So at 1 by t2, this is plus 20, sorry, this is plus 20 dB per decade. Okay, so at minus 1 by t1, this comes into play. We know that, this comes into play. We know that this offers a 20 dB per decade. After another at 1 by t2, what happens is this will come into play. So this will be offering a 20 dB per decade, while the denominator is offering a minus 20 dB per decade after T2. So what happens? Minus 20 plus 20, that becomes 0. So from this onwards, it will be offering a constant amplitude. Okay, constant magnitude or amplitude. Now, if you try to plot the this thing, right? If you try to plot the phase, so you can find the phase to be, say, when it comes, say, somewhere over here. So this will be arriving at so this will be tan inverse say omega t1 by omega t2. So as the this will be having a correlation between the phase and the magnitude, right? So this phase angle will be always equal to, the phase angle will be this is actually of a minimum phase transfer function. Do remember, this represents a minimum transfer function. This phase angle will be at omega is equal to infinity. It will be minus 90 into m minus n degree. Now what is this m and n? Where n is the order of the numerator, n is the order of the numerator, and m is the denominator polynomial. M is denominator minus numerator. Okay, so this is the order of this. So in this case, this is order is what? The order is 1. So this is 1 minus 1, which is equal to 0. That's why I have shown this as 0 degree and again a 0 degree. Okay, so that means there is a unique relationship between the magnitude plot and the phase plot for a minimum phase transfer function. Now when it comes to the non-minimum transfer function, that is of this form, you can see that the magnitude plot. What about the magnitude plot? When you draw the magnitude plot, this is one is 1 minus j omega t1, the other one is 1 plus j omega t2. Now when you draw the magnitude plot, you can say that, so this will be, you will be getting the same graph as we have find out here. So at minus 1 by t1, it will be offering a plus 20 dB per decade. At 1 by t2, this remains a constant. So that's it. While what you can find out in the phases, you can see that this phase is going to decrease as the, so this is how it goes. So there is no unique relationship that you can find between the phase and the okay. So for both the magnitude, we can see that this relationship is valid only for minimum phase transfer function. This is not valid for non-minimum phase transfer function. Now one more point is for both the cases, the magnitude will be always equal to, the magnitude will be at omega is equal to infinity, will be equal to minus 20 into m minus n decibel per decade. So in this case, m minus n is 0, so this is equal to 0 minus 0 dB per decade. That means as you approach to infinity, this no longer is having a gain for both the cases. Okay, so this is called as a minimum phase transfer function and a non-minimum phase transfer function. Now one more point is there, one more transfer function is there, that is called as an all-pass transfer function. And this all-pass transfer function, okay, all-pass transfer function is defined as, it is a transfer function which has a symmetric pole, and 0 symmetric pole and 0 about the imaginary axis in the S plane, okay. So it is having a symmetric pole and 0, right? So that means this is of the form say some g of s is equal to 1 minus st divided by 1 plus st. right? So here the 0 will be at 1 by t, while Paul will be at minus 1 by t. So anyway, where from the imaginary axis, you can see that 0 lies at a positive 1 by t, and this Paul resides at minus 1 by t, which means that the poles, so here you have the poles and here you have the 0. These distance are equidistant. Okay, so that is why symmetry. So there exists a symmetry along the imaginary axis. Now, what happens when you take the magnitude of this? When you take the magnitude, you will be having the same magnitude for the numerator and denominator, right? This is root of 1 square plus t square. This is also root of 1 square plus t square. So the magnitude will be equal to 1, and your 20 log magnitude will be 20 log magnitude 1, which is equal to 0. So this is the speciality of the, so when you try to draw the Bode plot for this transfer function, you can see that the gain will be always at 0 dB. There is no change in the gain. The gain remains at 0 dB, or you can say that the gain is always equal to 1. That means, what's the meaning of that? For all the frequencies, it is offering a gain. Okay, that means it allows all the frequencies to pass through, and because of this reason, this is called as an all pass transfer function. Okay, now what about its what about the phase? Now the phase will be, say, if you can convert this into 1 minus j omega t divided by 1 plus j omega t, the phase will be equal to tan inverse minus omega t, right, minus tan inverse omega t, right? So this minus tan inverse omega t becomes, you can bring this out. So this will be minus 2 tan inverse omega t. So this angle varies from 0 degree to minus 180 degree, as omega varies from 0 to infinity. That means, say, it will be, say, somewhere over here. So this will be minus 180 degree. This is 0 degree. That means you will be getting a graph something like this. Okay. So at omega is equal to infinity, you can see that. See, look at this. At omega is equal to infinity, what happens? Tan inverse infinity is 90. 90 into 2 minus 180. So at omega is equal to 0, it will be 0. So that means, as omega varies from 0 to infinity, the phase varies from 0 to minus 180 degree. Okay, this is going to be like this, while the magnitude remains at 0 dB. Okay, so the all pass filter, it is showing the nature of the all pass filter. All pass filter allows all the frequencies. That means it offers the same gain to every frequency, but as frequency increases, it offers a phase. Okay, hope you understood. So this is the concept of these three transfer functions. So the three transfer functions are minimum phase transfer function, non-minimum phase transfer function, and all pass transfer function. And hope you understood about the Bode plot of each type of transfer function. Okay.